that we can construct another random variable W prime on the same probability space so that the distribution of W prime is equal to the distribution of W prime and W. It's called they are exchangeable. And moreover, we assume the conditional expectation of their difference given W is a linear function of W where this lambda is a positive constant. So in applications, we always choose W prime to be a small perturbation of the original random variable W of interest. Therefore, typically W prime minus W is small and lambda is a small positive constant. So this is setting, and of course it's very special, but it has proven to be useful in many applications. So such exchangeability and the linearity condition may be motivated by considering a bivariate normal vector ZZ prime with mean 0, marginal variance equal to 1, and with a large correlation 1 minus lambda. In this case, it can be easily checked that ZZ prime has the same distribution as Z prime Z. And this linearity condition is satisfied for ZZ prime with the same constant lambda in this correlation. So therefore, if W is close in distribution to Z, hopefully in some cases we can have a same structure for W. So another example of this exchangeable pair structure is the sums of independent random variables. So here, Cc1 to Cn are independent mean 0 random variables, and W is their summation. We assume it's standardized so that variance of W equals 1. So a standard way of constructing exchangeable pair structure for this W is as follows. We let Cc1 prime and Cn prime be an independent copy of this sequence Cc1 to Cn, and we choose a random index I uniformly from 1 to n, and independent of everything else. Then we define this W prime to be W minus Cc capital I plus Cc capital I prime. So basically, we are randomly choose a summand and replace it with an independent copy. Therefore, it's understandable that based on this structure construction, W prime are exchangeable. And moreover, it can be verified that this linearity condition is satisfied with this small positive constant lambda equals 1 over n. So this 1 over n comes from taking expectation with respect to this random index capital I. So that's another example of exchangeable pair structure. So this is the main result of Stein. So he provided an upper bound for the Wasserstein distance between W and the standard normal Z, assuming this W has the above exchangeable pair structure. So this is the same setting above, and assuming that we have a control on the Wasserstein distance. So here Wasserstein distance between two random variables is denoted by this D sub W, and it's defined to be the sup of the absolute difference between E of HW and E of HZ, where this test function H is taken over all Lipschitz functions with Lipschitz constant 1. So this Wasserstein distance is of interest because it has connections to transportation distance. So this dW is actually equivalent to the minimum L1 norm of the difference between W and Z under all couplings. So that's a distance. And now we look at Stein's general upper bound for the distance, assuming the exchangeable pair structure. So it has two terms. To understand the order of these two terms, we first note that based on the exchangeable pair structure above, it can be deduced that expectation of the difference square of W prime and W equals 2 lambda. That's a direct consequence of these two assumptions. Then we first look at the second term in the upper bound. It's because square cancels with lambda, so roughly it's of order w prime minus w. For this bound to be small, usually we construct this exchangeable pair so that w prime is just a small perturbation of w. For the first term, note that this conditional expectation has the expectation exactly equal to 1 because of this result. Therefore, the first term actually measures the concentration of this conditional expectation around its average, which is 1. Usually we bound this first term by using Cauchy-Schwarz and bound the overall expectation by square root of the variance of this conditional expectation. So Stein provided this general upper bound for the Wasserstein distance between the exchangeable pair structure. So on the previous page, we had this exchangeable pair coupling for sums of independent random variables. So we can check what this result gives us for that special case. So for sums of independent random variables W as above, the previous general bound actually reduces to some constant times square root of summation of a force moment of the summands Ci. I mentioned that the force moment comes from exactly bounding this term by square root of the variance. So the variance of the second moment term becomes a force moment. So another thing is I'm using this capital C to represent absolute constants, so it can be computed explicitly. I just leave it there for simplicity. Another remark about constant is that I'm using 1 here. These ones can be made smaller. So for simplicity, I just replace it by 1. So now the general bound reduces to this one for sums of independent random variables. So to understand the order of this upper bound, we consider the case where Ci, this W is a standardized summation of a sequence of ID random variables. So Ci would be 1 over square root of n times xi, where this n is the number of terms, and xi is the underlying sequence of ID random variables. So we assume these x's have a finite bounded force moment. Then this upper bound becomes of order square root of n terms times this force moment. And because of this 1 over square root of n in front, it becomes square root of 1 over n. So the upper bound for this standardized sums of ID random variables is of order 1 over square root of n under bounded force moment condition. It's known that this order is optimal, although comparing with the classical Berry-Essing type bound in terms of sums of third of absolute moments without square root, here we need to impose a stronger bounded force moment condition. But this general result is useful beyond the independent case. So people have found many applications. For example, the binary expansion of a random integer, the anti-Volta model, the representation theory of permutation groups, character ratios, Erdős-Katz theorem, and degenerate use statistics. So our goal in this project is to extend the general Wasserstein bound in to multi-dimensions when the dimension d is larger than 1. And hopefully our general result can be of useful, it can be useful in as many applications. Okay, so actually this setting of exchangeable pairs has already been extended to the multi-dimensional setting by Chatterjee and Max and Reinert and Röhling. So it's very natural. Now we look at a d-dimensional random vector W with mean 0 and covariance matrix sigma. We assume that we can construct another random vector W prime on the same probability space such that again, W prime is exchangeable, and we have some linearity condition. Here, for the general purpose, they allow a small error term R in the linearity condition. And that term may not be an explicit function of W, so they also allow this condition in the conditional expectation to be possibly a larger sigma field than the sigma field generated by W. And also this coefficient lambda now becomes a capital lambda, now is assumed to be invertible D by D matrix. So if it's some constant times identity matrix, then this setting was proposed by Chatterjee and Max, and Reinert and Erling considered this more general setting of lambda being a possibly non-identity matrix. It looks very similar to the one-dimensional case, and it has also found the applications in many problems. For example, sums of independent random vectors runs on the line, doubly indexed permutation statistics, U statistics, subgraph counts in random graphs, and so on. So notice that all these applications are in the multivariate sense. So this is runs of different orders on the line. And this is a joint vector of permutation statistics, is a vector of U statistics, and the counts of possibly different subgraphs in random graphs. So this setting has also many applications. So therefore, it is of interest to obtain a similar Wasserstein bound, assuming your random vector W has this exchangeable pair structure. However, all the results in the literature are for smooth test functions. So for example, Max proved the following result. So for the above W, assuming this exchangeable pair structure, and for Z following a multivariate normal with mean 0 and the same covariance matrix sigma, and using D to represent the difference between this exchangeable pair W prime and W, she obtained this upper bound for the absolute value of expectation of HW and expectation of HZ. So the error bound depends on some part depending on the test function H, and also some other parts depending on this exchangeable pairs. So now we are looking at the test function H from RD to R. The quantity involving H in the upper bound generally is MKH. That is defined to be a soup of operator norm of the case or the partial derivative of H when it's viewed as a linear operator on K d-dimensional vectors, and then over all the arguments X. Here we only need M1 and M2. So M1 is just the Euclidean norm of the gradient of test function H. M2 is Hessing matrix, the operator norm of the Hessing matrix. So we see that we also need the H to be second order differentiable to apply this bound. Now there are other quantities involving W appearing in the upper bound. This R is a remainder in the linearity condition. So that's this R here. It's a d-dimensional vector, and we are using absolute value to represent its Euclidean norm. So that's first term. Then the second term involving the operator norm of the minus square root of the covariance matrix. So we are implicitly assuming this covariance matrix of W is non-degenerate, non-singular. Then there's a Hilbert-Schmidt norm of this D by D matrix represented by E. So sorry, I'm using this E for expectation. So hopefully there's no confusion. And this D by D matrix is defined to be the difference between the covariance matrix of W and the, again, conditional second moments of the differences. Then we have a similar operator norm of the inverse covariance matrix and third order term, or a third moment of the absolute value of the Euclidean norm of the difference between W prime and W. Okay, so that is a max upper bound. So it's easier to just compare it with Stein's bound for the one-dimensional case. So in D1, this was the result I stated before. So the terms involving W actually are very, very similar. So this E corresponds to this concentration of conditional second moments here, and this third moment of Euclidean norm of D corresponds to this third absolute moment of D in the one-dimensional case. So the only thing that's not entirely satisfactory is in Stein's upper bound, he only needed the test function to be Lipschitz with Lipschitz constant 1. So effectively, we can only assume M1H is bounded by 1. But in max bound, she needed a second derivative is also bounded. So that's why this result is only available for smooth test functions. It's known that if you have a smooth test function bound, you can deduce a Wasserstein bound from it. However, you will need to put a square root for the corresponding term. That makes the order not optimal. So in our main result, we have successfully removed the requirement on the second derivative of the test function. So that is our main result. We again have an upper bound for the Wasserstein distance now between two d-dimensional vectors, W and Z. It's defined similarly, so it's a sup of E of HW minus E of HZ, where now H is a Lipschitz function defined on RD, and with Lipschitz constant 1 with respect to the Euclidean norm. So this is again the minimum L1 distance between these two vectors. It's a natural generalization to the multidimensional case. So we have this upper bound. We have similar terms involving the operator norm of the inverse of covariance matrix. So we also need the covariance matrix to be invertible. And we have terms involving trace of this covariance matrix and slightly different terms in the third moment term. So it's easier to check the order when we look at the isotropic case where the covariance matrix is identity matrix. Then these operator norms all become 1. And this trace is D. So we have this D to the power 1/4 and times other terms. So to compare it with the previous bound, we see that the first two terms are the same. For the third term, we had to change the third moment of the Euclidean norm to something like a fourth moment, with a square root out of it. So I have to give some explanation about this different term appearing in our upper bound. So I have mentioned that when bounding this expectation of this absolute value of E or Hilbert-Schmidt of E, we usually use Cauchy-Schwarz and bound the square root of the variance of this term. Therefore, it seems not a problem to assume the finite force moment condition because we had to use that to deal with the E anyway. Now you may be worried that this term is this new term may not be of optimal order. To understand that, it's easier to look at the one-dimensional case where we recall that this equation following from the exchangeable pair structure. Therefore, if you had this third moment term, it's roughly of order just of order d, because d square cancels with the lambda. But although we have this square root outside, we have additional d Euclidean norm inside. Therefore, taking square root, we still end up with something intuitively same order as third moment bound. Therefore, we expect this change of the term is not a problem. So finally, it may be surprising, but in high dimensional cases, when the dimension grows with the sample size, fourth order error terms may even be preferable than third order terms. That will be illustrated in the following example. Okay, so that was our general bound. Now we talk about applications. So we apply it first to sums of independent random vectors. So here W is assumed to be, again, standardized sum of ID random vectors. We assume this axis has mean zero, covariance matrix equals identity, and the fourth moment of the Euclidean norm is of order d square. So the reason I consider this situation is because xi square has d terms, and when you take square of the square, there are d square terms, and each component of xi, each of the d components of the xi is assumed to be of order 1. So it's like d square terms of each of order 1. So it's in typical situations, this fourth moment will be of order d square. So another way to understand it is this xi is a d-dimensional vector standardized. So so typically its length is of order square root of d. So when I take fourth power, it's d square. That's why we consider this assumption to check the order of our upper bound. So it turns out that for the multivariate case, the exchangeable pair can be constructed exactly the same as in the one-dimensional case by replacing one summand in W by independent copy. And it can be verified that the linearity condition is satisfied with this coefficient matrix lambda equals 1/n times the identity matrix. In this example, our bound actually reduces to this order, which is square root of d to power 5/2/n. So we see that in terms of the sample size n, it's still of order 1/square root of n. So it's optimal, but there's a dependence on dimension appearing in the numerator. So to see how our general bound reduces to this one, so we have 3 terms in our upper bound. It turns out that the largest term is the third term. So we just check the order of this term, which is written here. So there's a d to power 1/4 in front, and then there's a square root. So this capital lambda is 1/n. So when take inverse, it becomes n inside. Then it's a fourth power of d. So here, that's the difference between the exchangeable pair d is this quantity involving, basically it's just xi. Then take fourth power, because each xi is supposed to be of order square root of d. And we have this normalization. Therefore, the fourth moment of d is typically of order square root of d over square root of n, and then to the power 4. That can be checked to be this order. That's why our general bound reduces to this order for the independent case. Now to illustrate that why this fourth moment bound can even be better than the third moment bound, we can do the same computation for the third moment bound. And it turns out that it's of order square root of d cube over n, which is worse than our bound in this typical situation. So that's the result for sums of independent random vectors. So you may wonder, is this order optimal or not? So it was shown by Zhai that the Wasserstein distance between the sums of ID random variables and the Gaussian variable has a lower bound of order square root of d square over n. This lower bound can be achieved. So therefore, there's still a gap in our upper bound and the lower bound. So recently, Eldan, Mikulinsa, Zhai, and Bonis, they proved a matching upper bound for even a stronger distance called the Wasserstein 2 distance. So our distance is Wasserstein 1, that's a minimum L1 norm. The Wasserstein 2 is a minimum L2 norm under all couplings. So it's larger than this DW. They proved a matching lower bound for this stronger distance, however, only under boundedness conditions. That means they assume xi Euclidean norm is uniformly bounded above by constant times square root of d. Therefore, it's still unclear whether the optimal upper bound is this one or this one under only finite moment conditions. So that's application 1. Now we turn to application 2, where we look at Wishart matrices. Now assume we have this m by n matrix xi, and assume the entries are ID with mean 0 and variance 1. So the Wishart matrix based on this ID matrix is defined to be 1 over square root of n times x transpose. This Wishart matrix is actually a m by m symmetric matrix. And we use Wij to represent its entry, its ij's entry. And it can be expressed like this. Now we look at the collection of the entries in the upper right corner of the matrix. It can be computed that all theseWij's have variance mean 0, variance 1 because of this standardization, and theWij's are actually uncorrelated, so their correlation equals 0. So we hope to approximate this joint vector of Wij by a multivariate normal, multivariate standard normal with a matching dimension. So we view this collection of Wij I less than j to be a vector, and we hope to approximate the vector by a standard Gaussian vector. Now the length of the vector is actually m choose 2, which grows with m. And the main problem here is how large can this m be so that jointly these Wij still converge to a normal vector. So I forgot to say that if you just look at one Wij, it's actually a standardized sum of ID random variables. So it's not surprising it converge to normal, where the whole problem is to look at increasing number of such Wij and still hope to get a multivariate normal approximation. So this problem was studied independently by Jiang and Li and Bubeck. Assuming these entries x11 of the matrix X follows a standard Gaussian distribution. So they had different motivations. So this is from random matrix theory, this is from a random graph theory. They found out this critical value. So if the n is of larger order than m cubed, then the the W is close to Z in total variation distance. And if n is less than that, you don't have approximation. I think there was a paper that tells what happens when n is a linear function of m's cube. That's still not normal. Then after that, Bubeck and Ganguly generalize the result to the case where x11 follows a log concave distribution. So it's more general than a Gaussian entry. Then after that, Nudan and Zheng considered relaxed the ID assumption of this matrix. They only assume each row, the different rows of this matrix X are independent, but each row can follow a Gaussian vector, Gaussian distribution with a general covariance matrix. And the Mikulinsa consider a case where the different columns are independent, but each column of X can follow a general log concave measure on Rm. They proved their result for Wasserstein 1 or Wasserstein 2 distance and found the same critical relation between n and m cube. So the question we would like to ask is all the previous results, depending on some special distribution of these entries, what can we say if we only impose moment conditions? So for example, some discrete entries, what can we do? So in some of these papers, they pointed out that a standard application of Stein's method only gives a normal approximation result for n is larger than or of larger order than n to power 6, which is not optimal. So applying our, so in this case, we can actually also construct an exchangeable pair coupling very naturally. So we have the original matrix X, we just randomly pick one entry in the n by n matrix and replace it by an independent copy and cause a new Wij created by this new perturbed matrix by W prime. So it can be checked that they are of course exchangeable, and it can be checked that linearity condition satisfies. Therefore, we can apply our general Wasserstein bound to this example, and what we get is following theorem. So that's a previous. That's basically the previous setting, and we assume the entries again have mean 0, variance 1, ID. But now we only impose a moment condition on these entries. That is, their six moment is bounded. Then we have this upper bound for the Wasserstein distance between W and Z, and we see that the correct relationship appears. So as long as n is of larger order than n cube, it tends to 0. Now the third application is to degenerate U statistics. So I first introduce degenerate U statistics in one dimension and of order 2. So the setting is as follows. We let x1, xn be independent and define W to be summation over all I less than j of some function small wij of 2 variables xi and xj. And we call this, the value of this function to be wij, which is a random variable. And we assume the things are standardized, so this summation has a variance 1. And what this degenerate means is this value given any either xi or xj, the conditional expectation equals 0. That is the same as saying if you do the Hofstadter decomposition for this W, the leading order term is 0, so it's degenerate. Therefore, in general, we cannot expect a central limit theorem to hold for such a W. But under special conditions, we can W is still close to normal, and it has connections to the famous force moment phenomenon. So it began with a work by de Jong, who proved that if this W has a force moment approximately same as a force moment of normal, standard normal, which is 3, And moreover, this rho square is close to 0, where this rho square is a maximum over or I of the summation over J of the variance of Wij. So that's a contribution of the variance of those terms involving a particular index I, and then taken maximum over all such I. This is supposed to be close to 0. This condition is actually corresponding to the classical central limit theorem for sums of independent random variables corresponding to the variance of each term should be close to 0. Each summand should be close to 0. That's a necessary condition. Then under this force moment condition and this, they say this maximum influence of each of these xi's should go to 0. Then this W can still be approximated by a normal distribution. That's the answer result. Both conditions are necessary. And then Dobler and Pecati proved the explicit upper bound for de Jong's central limit theorem by proving that the Wasserstein distance between this W and the standard normal is upper bounded by this quantity involving both of these two conditions. So it's square root of the difference between this and 3 and the square root of this rho square. And they have argued that these two terms are optimal order. So that was the literature for degenerate U statistic in one dimension of order 2. So you can imagine we can define similar degenerate U statistics of order P larger than or equal to 3. And we can even consider a vector of degenerate U statistics of possibly different order. So for example, we can consider W, now it's a D-dimensional vector, W1 to WD. Each of them is a degenerate U statistic of possibly different order, P1 less than till PD. Therefore, we can apply the, so it's of interest to obtain a similar Wasserstein bound between this vector and the multivariate Gaussian vector. So this is our result, so it's slightly complicated, but it's again involves a third moment condition for each component of this vector, and this maximum influence quantity. And for multidimensional problem, we also had this additional term, which not only needed the force moment of each component to converge to 3, also needed the expectation of Wj squared, Wk squared to close to the expression for multivariate normal. Sorry, there's some noise. Unexpected phone call. So I hope you had enough time to look at this upper bound. So it involves some additional terms beyond which is special for multivariate approximation. And these is actually also necessary. So I want to say that for this example, actually all the exchangeable pairs and the necessary computations were all done by these authors. What we did was only applying our Wasserstein bound directly to this problem. So in the next part, I plan to talk a little bit about the proof of our main result of this Wasserstein bound. So the method we use is Stein's method. So the proof sketch will have 5 pages. So the first 3 pages are what was done in the literature, and the last 2 pages were what we did. So recall that we have this exchangeable pair setting for our random vector W. So our aim is to approximate W by multivariate Gaussian vector Z with the same covariance matrix sigma. So the starting point to do this approximation is to consider this so-called Stein equation for multivariate normal distribution. Here it's a functional equation, and given the test function h, we are supposed to solve f from this equation so that the equation holds for every w in RD. So here z is a multivariate normal, and here w dot gradient f is the inner product, and this sigma Hessian matrix Hilbert-Schmidt norm is actually like the inner product of two d by d matrices. So it may look very strange, but it was motivated by considering this left-hand side to be the generator of some diffusion process with Z being the stationary distribution. So therefore, we can hope to have a nice, have a solution for this equation, which has nice properties based on the property of H. So it turns out that we have this explicit solution F for the above equation in terms of the integral from 0 to 1 over S, and then the integral in RD of this involving this phi d, which is the standard normal density function. So the sigma half times z is a normal with covariance sigma. So this is the solution. So you may be worried that this integrability issue when s is close to 1. What happens is when s is close to 1, this difference after integration over z is close to 0. That there will be no problem when h is sufficiently smooth. So that's a solution, and we have properties of this solution. So recall mkh is an operator norm of case order derivative of the function h over all arguments. We have these relationships between mkf, the solution, and the mkh, the test function. So m1f is bounded by the first derivative of f is bounded by first derivative of h. So it's easier if you just imagine it's a one-dimensional problem. So second derivative is bounded above by first derivative of the test function times this operator norm of inverse square root of the covariance matrix. And the third order derivative of the f is bounded by second order derivative of h times that. That's precisely where Max had this second order, had this dependence on the second order derivative of the test function h. So actually, you can easily see this upper bounds from the solution itself. So when you take a derivative of f, you have h prime. Then square root of 1 minus s will come out. The whole thing is integrable. That's why you have this. When you want to associate the second derivative of f with the first derivative of h, you have to will have this h double prime. Then you have to do a integration by parts to move one of the derivative to this Gaussian density function, and as a consequence, this sigma inverse comes out here. That's why you get that. This 1 over square root of s also comes out when you do the integration by parts, but that is integrable from 0 to 1, so that's not a problem. So the problem for that is for the third relation is when you take third order derivative for f, you have to do integration by parts 2 times if you want to get h prime. But then 1 over s will come out, and that's not integrable. That's why you only have you cannot replace it by M1H here. Then recall what we want to bound is E of HW minus E of HZ. So what we do is we just, this is the equation holds for all W. So we replace small w by capital W, and we can equivalently bound the expectation of the left-hand side. That is this first equation here. Then there's a standard, so now this thing only involves W and the solution F. It is a standard application of exchangeable pair setting to do some rewriting of this quantity using these quantities R, E, and then you get this third order derivative term. That obviously comes from using Taylor's expansion. So what we want becomes this summation of these three terms. Then we can just use the property of this gradient f, Hessing f, and the third order derivative of f to obtain an upper bound. That eventually leads to max bound. Okay, so let me quickly go into what we did for the modification. So the problem, as we see, is H is not sufficiently smooth when we talk about Wasserstein distance. So we can only have M1H is bounded by 1. So it's a standard idea in Stein's method to first smooth it. And a standard way to smooth the test function is to convolute it with a Gaussian vector, a small Gaussian component. So we define H epsilon omega to be the original thing plus epsilon z, where z is a multivariate Gaussian vector with a covariance sigma, and epsilon is supposed to be a small positive constant. So after doing that,
3 minutes. Yeah, 3 minutes.
3 minutes.
Yeah.
So it's a standard smoothing of the test function. Then what you bound becomes a smooth function bound plus the error introduced by this smoothing. Then you work similarly, and the only change is we had this problem for this third order derivative. We even go into fourth order derivative. So way to do it is, this is actually the key quantity we want to bound. What we do is we use exchangeability again to switch the position of W and W prime. Then this D will become minus D. So we have a minus sign in front because there are 3 terms and then similar terms. Now because this Kasi doesn't change after this switching by the exchangeability assumption. So this Kasi is actually average of these 2 terms. That's why you get this half its original term minus this term. The minus comes from the switching. Then you go into the fourth order terms. Therefore, actually the derivative of solution becomes worse. However, what you gain is the additional factor of D in the other term, so where D is supposed to be small. And balancing these 2 terms eventually get our result. That's why you get you have this epsilon here, but 1 over epsilon for the other term. So we get a square root of that fourth moment term in the end. So that basically is a proof of our main result. I planned to talk about some recent results on the general problem I stated at the beginning, but I guess I don't have time for that. But I have sent the slides to the organizers. So if you're interested, you can just read the slides. I think it's quite complete. So that's all for my talk. Thank you.
Thank you very much. All right, we can ask a couple of quick questions. Any questions?
Yes.
Yeah. Okay.
I have
Yes,
one.
please. Yeah, please.
In the Wishart example, in statistics, of course, you take away the means before you construct the statistic. So there's some additional dependency, which is sort of thought to be small. Can you handle that as well?
I haven't tried. I'm not sure. But
It sort of
depends on
morally,
whether,
you're right.
depends on you whether you have a exchangeable pair coupling for that. I don't know.
Oh, I see. Okay. Right. Tricky.
What,
Xiao, what can you say, like, so in all of these, in your bound, you have this sigma to the negative 1/2 showing up every.
Sorry, can I go back to Andrew's question? I think the same method works for nonlinear statistics because you have this. It's a function of independent random variables anyway. You can do this. You can do this exchangeable coupling. The only new idea in our proof is this. This step where it's crucial that you can do this switching to go into the fourth order derivatives.
Right.
Hopefully you can still deal with nonlinear statistics. Sorry, Nathan.
Nathan, what's your question? Nathan, could you please repeat your question?
Sorry, what can you say if sigma, if you don't know if sigma is invertible, the covariance matrix?
So that's that's a good question. Our result relies crucially on the invertibility of sigma because we want to do the integration by parts. If sigma is not invertible, probably you have to do some thing for before applying our result. For example, if you have a long vector, maybe the major contribution comes from a subset of these components, and the other components are small. Then you have to control Wasserstein distance. Maybe you first just do trivial things for those small components, then apply the invertible trick to the remaining components. I'm not sure, but our main result relies on the invertibility issue.
So do you know that for which one was the, you have a sigma to the negative 1/2 in one of your applications, right? For the, was it the degenerate U statistics, right?
Oh yeah.
So is that like, do you know that's in, is there some result that says that sigma is invertible for this theorem? Or is it like, if sigma is invertible, then this is the bound?
No, in general, I think sigma may not be always invertible.
Okay. Okay. Sure. I mean, the bound still works, right? If sigma's not invertible, but it's not a very useful one.
All right. Are there any other questions?
So is the methodology that you take robust to be generalized to infinite dimensions to say something about convergence at the level of processes?
So if I consider infinite sequence, so I can only imagine you have an infinite sequence of infinite sequence of random variables. Their variance has to decay to 0. So I guess it's related to my answer to Nathan's question. Somehow you have to do some truncation to work with in the finite dimensional case. Then do something else for the remaining part, I guess. Does it make sense?
No, I mean, instead of Z being a finite dimensional Gaussian vector, for example, if Z is a Gaussian process, can we obtain some estimate between the distance between an approximating process and a Gaussian process on the space of paths?
If the distance is characterized by finite dimensional approximation, then our result may be useful in that step. The approximation for the whole process, I'm not very familiar with.
Okay. Any more questions for Xiao? Okay, if there are no more questions, let's thank Xiao again for the interesting talk. Thank you.
Thank you.
All right, is this the last seminar for this year, course year?
I believe so, but
All
hopefully not the last one for this financial year.